Welcome to Lesson 1, Number Systems. In this lesson, we're going to explore our number system, the decimal number system, in order to appreciate what happens in a different number system, specifically in this case, the binary number system. So let's get to it. All right, so if I were to give you a number like this, you would probably say it's 333. And I would ask you, why is this 300, this one's 30, and this one is 3? Well, that's because each of these numbers exist in a specific position. So with all number systems, there's an inherent value to the number depending on where it is. So we know that this is called the hundreds place, this is called the tens place, and this is called the ones. Now we're talking about our number system, the decimal number system, which can also be called a base 10. So why base 10? Well, there's two reasons for that. First one is that in each position, we can have one of 10 possible numbers, that being 0 to 9. Another reason for it to be called the base 10 is that each of the place values can be represented as some number with a base of 10. So let's think about that. So if each of these numbers, place values, have a base of 10, what's the exponent? So in order to get to 100, this would be 10 squared. In order to get to 10, this is 10 1. And one that might elude some students is that 10 to the 0, something to the 0 power is 1. Now this is key because in every number system, it really doesn't matter what the base is. Your exponent to 0, that base raised to the 0 power will always be 1. Okay, so we understand this idea of place values. That's the reason this one's 300, this one is 30, and this one is 3. But let's go a step further, putting it all together. So in a number system, to kind of get the full value of what the number is, we take the digit that's at that position, we multiply it by its place value, right? So we do 3 times 10, that's equal to 300. We do 3 times, did I say 3 times 10? 3 times 100 gives us 300. 3 times 10 gives us 30. And then 3 times 1 gives us the 3. And then what do we do with all this? We add it up and we get the 333. Now again, we take it for granted that we work with our number systems so much that we don't think about this process. But this is something you're going to have to appreciate when we move into another number system which we're not familiar with. So again, remember this process that each place value gets multiplied by the value in that particular position, and then we add it up. This is the process. This is how we do it. All right, so let's talk about the binary number system. So how does the binary number system work? So we're going to start with the word binary. So the word bi means 2. So binary is a base 2 number system. Now, kind of going with the analogy to our decimal system, base 10, this system only has 2 numbers. It has 0 and 1. That is it. The other thing that's important here is that means that every number, every place value in this system is some power of 2. So going back to our analogy from the decimal, we're going to put 2's in each of these place values. And the first position will be 0, just like it was in our other one, which was, the 1. This one's going to be 1, 2, 3. All number systems behave this way, where it's the base and then just slowly increasing the exponent with each new position that gets added to the number. Now again, this isn't our number system, so we're not familiar with the place values. But we might be more familiar if we do this now. 2 to the 0 has a value of 1. 2 to the 1 has a value of 2. 2 to the 2 has a value of 4. And 2 to the 3 has a value of 8. Now once you start going here, you might say, well, how am I going to calculate these powers, 2 to these powers? Well, if you kind of notice what's happening, each time we're simply multiplying by another 2. So really, to get from one number to the next, you simply multiply them by 2. So this is 2, 4, 8. You kind of guess the next one is 16, and then 32. And this might be a little easier for you to remember than for you to actually sit there and say, okay, what's 2 to the 4? What's 2 to the 5? It's probably easy for you to remember these positions down here. Okay, so we have an understanding of the place value. Again, that's important in any number system. Now let's talk about what a binary number could look like. Again, going back, we can only have one or two numbers, 0 or 1. So I could do something like this. I could put a 0 here, a 1, 0, 0, 1, 0. This is a binary number. But what does that binary number mean? To us, anyway, something that we can understand. So just like in the other example, we take each digit in a particular position and multiply by its place value. So we'll say 0 times 2 to the 5 equals. Now here's the interesting thing. 0 times anything gives us 0. And ultimately what we're going to do with all these numbers is we're going to add them up. So I would say anything that has a 0 in that particular position, there's no need to include it as part of your calculation. Again, it's going to be pointless because you're adding 0. So let's kind of go on. So we go 1 times 2 to the 4. And what is 2 to the 4? It's 16. So 1 times 16 gives us 16. Going back to what we had just said, there's a 0 here, so there's no need to include it in our calculation because it's just going to end up with 0. So we see that our next possible value would be this one, which is the 1 times 2 to the 1, which gives us 2. We add it all up and we get 18. So this number in binary is 18 in decimal in our number system. Hopefully you can see the correlation to our discussion with the decimal number, which felt overly elementary and almost confusing to the point because we had to break it down like that. But now you can see why we have to do that. You have to understand the place values and the process by which we can figure out the total value, which is simply by multiplying the digit in that location by its place value. Now I will tell you, this is a lot harder than this next way I'm going to show you how to do this. Like we said, anything that has a 0 in it doesn't affect our result. But the things that have 1s in it, the positions that have 1s in it, will affect our result. So instead of going through all that multiplication, realizing that the only number we could possibly have in a particular place is a 1, why don't we just simply add up the place values? So doing this, I can see here, I'm going to skip the 32. I'm going to add up the 16. I'm going to skip the 8. I'm going to skip the 4. I'm going to add up the 2. And I got my answer of 18. So this means that 0, 1, 0, 0, 1, 0 in base 2 is equal to 18 in base 10. Now, usually when you work with different number systems, they'll use a subscript to denote the base, so that you can appreciate that this is a binary number. And let's say if I left off the leading 0, that you wouldn't confuse this with 10,010. Right? This is not 10,010. This is 010010 in binary, which is 18 in our number system. So that is the basis of our number systems and how to convert from one to the other. I will do one more example, and that's how to go the opposite direction, which essentially is the same thing. So what we're going to cover now is how to go from decimal to binary. Because right now what we just did is we converted binary to decimal. So now we got to go the other way. So let's say we had a number such as, let's say 65. We'll keep it simple. Okay, so this is our number in decimal. Let's convert it to binary. So let's set ourselves up. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. I'm not quite sure how many positions we're going to need, but I'm going to set ourselves up for 8. There's also another reason, which I'll explain at the end. Let's put our place values. And we, again, just to reiterate what these place values are, this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. Again, if I were to ask you, what is 2 to the 7? You might sit there like, honestly, so am I. So the easier thing to do is simply to start with the first one and just simply keep doubling it. So 2 to the 0 is 1, 2 to the 1 is 2. That's easy. I would even gather that most of you could get to 2 to the 2 without much problem, even 2 cubed, which is 8. At this point, it might be easier just for you to realize, just simply multiply each number by 2, because that's what's happening. And then work with these values instead. So our goal is to get to 65. All right, so if I was to put a 1 here, that means I have 128. So that's too much. So obviously I cannot have a 1 in this position. I got to put a 0. I do not want any 128s. Now let's move over to the next one. 64. Okay, so if I was to put a 64 here, well, that works for us because I'm trying to get to 65. And so far now I have 64, which means I only need to get 1 more. So that means I got to put zeros in the rest of these and then a 1 in the very last position. So this number, 0, 1, 0, 0, 0, 0, 0, 1 in binary is 65 in our number system. So you might be curious as to, why did I include the 128? It's too big. We knew we weren't going to use it. The reason for that is that the way a computing device stores its memory, it stores its memory in something called a byte. And a byte is equal to 8 bits. Each of these digits is called a bit. So that's the reason why I expressed it as 8 bits, because that is the smallest unit of memory accessible by a computing device. So if you ever run into this situation where you don't have numbers in front, then you just have to pad it with zeros, just so that you get that understanding that this is how the computer will read the information. So let's go back to our presentation. And let's review what we've done. So we discussed number systems, specifically the decimal number system and the binary number system. The decimal number system is the system that we're familiar with. Binary number system is the system that's used to communicate with computing devices using machine language. So hopefully at this point you're able to kind of understand how ultimately whatever we create has to communicate with a computing device, and that you now can do it as well. Enjoy.